Good day to Dr. Arif. Today we are going to present about T3 Joule-Thomson effect. First of all, let me introduce our team members. I am Shin Er, and my other team members are Aisyah Farzana and Ayu Asmida. There are three main objectives in this experiment. The first one is to demonstrate the principle of gas cooling by expansion. Second is to demonstrate the throttling process. And the third one is to demonstrate the Joule-Thomson principle. The apparatus that we will use in this experiment including Joule-Thomson apparatus, temperature probes, digital meter, carbon dioxide gas, and also nitrogen gas. Joule-Thomson effect describes the temperature change of a real gas when expanded through a throttling device. During the throttling process, the gas flows from a high pressure region to a low pressure region through a small restriction. The main characteristics are there is no heat transfer, no external work is done, and the enthalpy remains constant. At the same time, the pressure decreases. As a result, the gas temperature might either increase or decrease depending on the gas type and initial condition. The throttling process is explained as constant enthalpy process, where the enthalpy before the expansion is equal to the enthalpy after the expansion, represented as H1 equals to H2. The Joule-Thomson coefficient is used to describe how the temperature changes with the pressure, and it is written as mu equals to delta T over delta P. If the mu is positive, the gas cools during the expansion. If the mu is negative, the gas heats up. Meanwhile, if the mu is equal to 0, there is no temperature change during the expansion process. The temperature measurement system was prepared before starting the experiment. First, the digital temperature meter was switched on 30 minutes earlier to allow it to stabilize. Then, the T1 probe was connected to measure the temperature at high pressure region. Next, the T2 probe was connected to measure the temperature at low pressure region. Before taking any measurements, the LED indicator for both probes were checked to ensure that the probes were working properly and ready for the experiment. The measurement procedure using carbon dioxide and nitrogen gas was carried out carefully. First, all valves were closed before the selected gas cylinder was connected to the Joule-Thomson apparatus. Then, the cylinder valve was slowly opened, and the pressure reading was checked. The reducing valve was adjusted to the set initial pressure, which was 0.8 bar for carbon dioxide and 0.9 for nitrogen. After the temperature readings became stable, the delta T values were recorded. The pressure was reduced by 0.1, and the measurement was repeated until the P1 reached 0.1 bar.
Hello everyone, so we will move to the data analysis and calculation part. The first part is CO2, which is the first one we need to convert the pressure to absolute pressure, which is pressure plus 1.0. 1.0 is PATM. So we got the CO2 data, and P absolute is X and data temperature is Y. After we get X and Y, we can determine the S squared and SY by calculate both of data. And then we got sum of X, which is 11.6, sum of Y, 2.74, sum of S squared, 17.24, and sum of XY, which is 4.314, and N, which is 8. Now after get the data, so we can calculate the gradient, y-intercept, and centroid. So if you want to calculate this, you can put the value inside the formula given, which is in least square method. This table is for CO2, which is we do the least square method to we need define the uncertainty for CO2, which is uncertainty gradient and uncertainty y-intercept. So we just calculate as usual using the same formula given, and then we get these values. So in this part is the calculation for to define the uncertainty for gradient and also y-intercept C. So we just calculate from the formula given, and we can finally get the gradient uncertainty and also y-intercept uncertainty for CO2. So this is the graph of for CO2. So basically we can just do the graph for y delta t and x for pressure absolutes that we already determined in the table. So here is N2 part. So again, we need to convert P to P absolute to the pressure absolute, which is P the pressure plus with PATM, which is PATM equal to 1.0. So we can determine the P absolute, which is X, and delta T, delta temperature is Y. So from the calculation in the black box, we can get the summation of X, summation of Y, summation of X squared, sum of XY, and N, which is equal to 9. So this part is similar how we calculate in CO2, which is we need to find the gradient, y-intercept, and also centroid for N2. So this is the way how we need to calculate the uncertainty for gradient and also y-intercept by using LSM least square method. So we can just put the value inside of formula and get the value. So this is the graph that determined from the N2. So after we calculate all the values, so we can manage to sketch the graph, to draw the graph. Now we will move to second analysis, which is determine the Joule-Thomson coefficient for the case, and the uncertainty. So the first step is from the equation 7.2, we need to differentiate the 7.2 equations to 7.3 equations. After that, we can calculate the percentage uncertainty for CO2 and N2. So this is last question for data analysis and conclusions. So okay, by using the equation 7.6 and this table 3 below, so we need to find the coefficient for CO2 and N2. After we get the coefficient, so we can compare the theoretical and experimental value of CO2 and N2.
As for the discussion, I will just briefly summarize the main points. Firstly, in this experiment, nitrogen gas and carbon dioxide gas were allowed to expand from high pressure to low pressure through a throttling valve. The process happened under nearly adiabatic condition, which means there was very little heat transfer to the surroundings. No external work was done during the expansion, so the enthalpy remained almost constant. After the gases expanded, the temperature of both gases decreased. This cooling effect happened because of the intermolecular forces between the gas molecules. Since both N2 and CO2 cool during the process, they have positive Joule-Thomson coefficient at room temperature. For the first analysis, a graph of temperature difference against pressure difference was plotted for carbon dioxide gas. The graph showed a positive linear relationship where the temperature difference increased as the pressure difference increased. This means that carbon dioxide cooled during the throttling process. The positive slope also shows that carbon dioxide has a positive Joule-Thomson coefficient at room temperature. This means the gas temperature decreases when the gas expands at constant enthalpy. The cooling happened because of the attractive force between the gas molecule during expansion. For nitrogen gas, the graph showed a small negative gradient. This means the temperature difference decreased slightly as the pressure difference increased. So, nitrogen gas experienced very little cooling and may have undergone slight heating during the expansion process. The negative slope shows that N2 had a negative Joule-Thomson coefficient under the experimental condition. This happened because nitrogen is close to its invasion temperature at room temperature. Compared to carbon dioxide gas, nitrogen gas also has weaker intermolecular forces, so the temperature change during expansion was smaller. From the experimental result, the Joule-Thomson coefficient for carbon dioxide was 0.812 plus minus 0.019 times 10 power of negative 6 Kelvin per Pascal, which confirms that carbon dioxide cooled during expansion. For nitrogen, the coefficient was negative 0.21 plus minus 0.13 times 10 power of negative 6 Kelvin per Pascal, showing that nitrogen experienced was very little cooling or slight heating during the process. The uncertainty for nitrogen was quite large compared to its coefficient value, which means the readings for nitrogen were less accurate because of the temperature change was very small and difficult to measure precisely. The theoretical values obtained were 2.460 times 10 power of negative 5 Kelvin per Pascal for carbon dioxide gas and 7.316 times 10 power of negative 5 Kelvin per Pascal for nitrogen gas. The percentage difference for both gases was about 99.7%, showing a large difference between the theoretical and experimental result. There were several sources of error in this experiment. First, heat exchange with the surroundings may have occurred, causing the process to not be perfectly adiabatic. Pressure fluctuation during the throttling process could also affect the accuracy of the reading. Besides that, human error during data recording and graph plotting may have caused inaccuracy in the result. To improve the experiment, the temperature and pressure reading should be taken carefully and consistently. The apparatus should also be properly insulated to reduce heat transfer from the surroundings. In addition, the experiment should be repeated several times and the average value should be used to reduce random errors. In conclusion, the objectives of the experiment were achieved. The experiment showed the gas cooling by expansion, the throttling process, and the Joule-Thomson principle. When the gases expanded from high pressure to low pressure through the throttling valve, the temperature changed even without heat transfer with the surrounding. But nitrogen and carbon dioxide gas cool after expansion, but carbon dioxide showed a bigger temperature decrease than nitrogen. The experiment also showed that the enthalpy remained approximately constant during the throttling process. Here is the list of the references of this experiment.